Hello, everybody. My name is Ahmed Mahmoud. I'm a PhD candidate at University of California, Davis, and a senior research scientist at Autodesk Research. In this work, we developed a GPU mesh data structure to speed up geometry processing application by leveraging the GPU massive parallelism. As this work targets triangle mesh due to its ubiquity in so many applications, from simulation and modeling to visualization and 3D printing, and so many other computational geometry applications. And in order to use the GPU to speed up triangle mesh processing application, we offer a programming model that is intuitive, provide a high-level abstraction for a large set of mesh processing application. We also provide a data structure that can perform a query operation with high performance on the GPU while being generic and compact. Our programming model is focused on applications that require computation based on local neighborhood. And our programming model is quite simple. However, we believe it's powerful enough to implement a diverse set of applications. Using our programming model, the user only thinks of the local operation applied to a single mesh element. This operation may involve a query operation to the adjacent and the incident mesh element, or query to the mesh attributes. So under our programming model, the user responsibility is just to composing this computation by defining what computation a single mesh element should perform. The implementation of the programming model then takes this computation, run it in parallel in all mesh elements in such a way that maximizes locality, induces load balance, and eventually leading to higher throughput. And what enables us to deliver this high throughput is the data structure. When we designed our data structure, we set forth a couple of design decisions, with performance to be the #1 priority. Generality in terms of being able to handle non-manifold meshes comes second, and then being compact. In order to meet this design goal, we follow a couple of design principles. The most important one is how we improve the locality. While global sorting of the mesh element is the standard method for capturing locality when working on the CPU data structure, we found that this is not the optimal solution for the GPU due to the limited L1 cache size. For this, we opt to a different approach in order to capture locality, which is batching. With batching, we divide the mesh into small patches that can fit into the shared memory and perform all the query operation within this shared memory. This guarantees that we always exploit the memory with the highest bandwidth. We represent every batch using the linear algebraic representation, which can be used to represent any simple shell complex. However, we optimized it for triangle mesh. Using this representation, we only store two very sparse matrices, and all other query operations are performed as a matrix operation. This representation enables us to come up with a new way of assigning work to computational threads, where threads work collaboratively in order to perform the query operation. This means the query operation will balance something that is not achievable using alternative representation. For evaluation, we have implemented 4 applications. Each one of them test and explore a certain aspect of the data structure and the programming model. For some application, like mesh smoothing, RXMesh outperform a well-optimized version of directed edges data structure by more than 4 times. And this can go even higher, up to 15 times, being 15 times faster in geodesic distance application. In other application, RXMesh perform on par with other data structure. And so we think RXMesh strikes a good balance between different computational patterns that we have encountered in our application. The conclusion we drew from this work is that the programmer managed caching using GPU shared memory is the right way to improve performance when it comes to mesh processing on the GPU. Thank you.